trotzdem irgendwie das vierte Buchstaben in Formel nicht verstehen.
Can everybody hear me now? Good. Okay. So, good evening. It's very hot, so I'll try to make this as easy as possible, but unfortunately some parts will be hard. Apologize in advance. So I'm going to talk to you about mineral description principle, and before I start, to give an overview of what I'm going to do in the following 4 lectures, let me give you the basic idea. What is this all about anyway? So, mineral description length, or MDL, is a principle for inductive inference which has been developed mainly by Jorma Ritzman over the last 25 years. You can use it for all kinds of inductive tests like parameter estimation, cross-string prediction, but it is mostly developed and it's mostly well suited for model selection problems. So these 4 lectures are going to be concentrated on model selection problems. And what I'm going to do first is give you the very basic intuitive idea of MDL, what it is based on, and say a little bit more about its main application, model selection. So the basic idea of MDL is that there is a certain correspondence between regularity in a sequence of data or a sample and ability to compress it. In other words, the more you're able to compress a given sequence of data, the more regularity it can be said to have detected in the data. This is an information theoretic idea which will later be formalized, but for now let me just give you an intuitive idea of what this means and whether it makes any sense. So let's first look at a sequence that's intuitively very regular. It has a clear pattern in it. So this sequence, think of it as a 100,000-fold repetition of 001. Clearly very regular. If the idea is to make any sense, then this sequence should be very compressible, right? Very regular. Is it compressible? Well, in fact, I've already compressed it for you. Because to write out the sequence in full, it would take you 300,000 bits. I've given you one sentence of natural language, which allows you to unambiguously reconstruct the whole sequence. And this one sentence of natural language is, of course, a lot shorter than the sequence. Now, natural language is an informal way of describing things, but I could also think of a more formal way, for example, a computer program, which would print the sequence in that whole. Still, such a computer program would be a lot shorter than the sequence itself. So here we have a very regular sequence, which is very compressible. Now let's think of a very irregular sequence, or at least from an intuitive point of view, irregular. So suppose here I have 300,000 bits generated by independent Faircoin topics. If the idea is to make any sense, then that sequence should not be compressible. Now it turns out that you can show that with extremely high probability, no matter what encoding method you use, the sequence is hardly compressible at all. Now why is it so? Well, first I have to explain to you what I mean formally by the description of the sequence. It turns out that you can do without loss of generality descriptions by binary sequences. So what happens here is that the description method or code is just a mapping from these data sequences, in this case length 300,000, to alternative binary sequences. So each data sequence gets mapped to some encoding of it, which is another binary sequence. Now there are only 2 binary sequences of length 1, only 4 binary sequences of length 2, only 8 of length 3, etc. However, there are 2 to the 300,000 binary sequences of length 300,000. So this means that only an incredibly tiny fraction of them can be compressed to 1 bit, or 2 bits, or 3 bits. More in general, there are 2 to the power k sequences of length k, 2 to the power m sequences of length m. So of those, only a fraction of those 2 to the power m sequences, only a fraction of, let's say only a fraction of 2 to the minus k can be compressed by k bits or more, because there's simply not enough binary sequences you can map all the long sequences to. Now, if the sequence is indeed generated by a Faircoin, then all sequences are equally probable. So this means that the probability of the sequence is simply 1 over the number of sequences. And this means that no matter what coding method I use, the probability that I can compress a sequence by more than k bits is smaller or equal to 2 to the minus k. So, for example, the probability that I can compress the sequence by more than 100 bits is already smaller than 2 to the minus 100, which is completely negligible. So here we have a very irregular sequence, random sequence, which is indeed incompressible. I've seen that the more regularity I can find, the more I can compress the data. So maybe it's useful to think of learning as trying to compress the data as much as possible. That's the basic idea of MDL. We're going to test learning in terms of compressing sequences, and then we're going to see whether this is useful, whether this brings us in. That's the basic idea of MDL. So we're going to apply it mostly to model selection, and by this I mean something which I'm sure you've seen last week. So suppose I have a sequence of data, and as is customary in information theory, I denote a vector of data like this. X sub n is the sequence outcome. Now I contemplate different explanations for the data, and I want to select one of these explanations as somehow the best explanation. Now it's well known that if the model's explanations you contemplate for your data can be arbitrarily complex or flexible, then it's not good enough just to take the model that somehow best fits the data. You somehow need to regularize, take into account complexity or flexibility of models. So an example is, for example, if you have binary data, you want to find not just as the ordinary statistics, let's say the best Bernoulli distribution for the data, or the best first order Markov chain, but you also want to learn from the sequence what is a good order for the Markov chain to be referred. How many bits do I have to look back? How many dependencies do I have to allow to account for the sequence I've seen? So another typical example is, of course, regression. I'm sure you've seen these pictures before, but just a feel where we're heading. General game is this. So suppose I have two-dimensional data, x points and y points. I want to find a relation between y and x. A very simple thing I could do is try to fit the best straight line. For example, using these squares fitting. And you get something like this. Now this clearly gives some of the trend in the data, but perhaps not all. So I might want to go to more flexible models. For example, a set of all polynomials. So then I would try to look the best polynomial on a set of all polynomials to each degree for the particular data set I have. So then you have from overfitting, if you have n data points, there's always a polynomial of n minus first degree, which goes through all these points. So you get something like this. And here you're just fitting the noise here. You're not finding the pattern in the data. So at least intuitively what you would hope for a model selection to do is give you something like this. A relatively simple polynomial, not too high degree, that is non-zero but small errors and compromise between complexity and goodness of fit. And so we'll hope that MDL will do something like this. Now, you might have noticed that in the very first slide, this talk was called Introduction to Modern MDL, and it also had the subtitle Universal Models. Now, why is it so? Unfortunately, perhaps there are zillions of types of MDL. Grünwald, whenever he came up with a new version, priced in that MDL and didn't think of the earlier versions anymore. This has caused a lot of confusion in the literature. So I want to stress that I'm focusing here on, say, the newest version, which is in a sense kind of a confluence of many earlier versions. And it's based on the statistical idea of the universal model. It has been developed in the mid-90s, and it's actually quite different from what many people think MDL is. All the versions are now simply viewed as kind of approximation. So this is what I'm going to talk about. And I'll explain at length what the universal models are. So in the 4 lectures to come, in the first lecture, so that's now, I'm going to do the remaining minutes I have to give you a crash course on information theory. Because there are certain aspects of information theory which you just have to know. If you don't know them, then there's nothing else. You just can't understand the code. So that's really crucial. And I'm just going to hint at how you're going to use middle description and model selection with the information theory knowledge I gave you. Then in the next lecture, I'm going to talk all the time about MDL model selection. Then in the 3rd lecture, I'm going to go beyond model selection. In the 4th lecture, I'm going to talk about specific use of MDL for classification problems. So we start with the information theory. And there are really just 2 parts you have to know. 2 parts of information theory. And forget about the rest. First of those is the relationship between probability distributions and code lengths. That underlies everything, all of information theory. The second is this magical notion of universal model. Let's start with the relation between probability distributions and code lengths. So when in this talk I use the word code, I always talk about the following setting. I have some set of outcomes, which is typically called data alphabet. And I'll assume for now that it's finite or countable. Later I'll look at continuously valued data, but for now assume it's countable. Now a code is a map from its data alphabet to the binary sequences of length 1 or longer. So I'm going to map everything to a binary sequence. And when I speak of codes, I mean what information theorists call uniquely decodable codes. So the codes I'm talking about are always such that if you have a description of an outcome, so you map this outcome in X to a binary sequence, given the description, you can uniquely reconstruct the outcome that gave rise to the description. So it's lossless coding. MDL is about lossless, not lossy coding. Now, given such a uniquely decodable code, which is called code, I use this notation to denote the number of bits needed to describe an outcome. So, given a code C, L sub C of X, it's just how many bits I need to describe this particular X. Note that this must always be an integer. So here's a simple example. Suppose that this has 4 possible outcomes. Something like wrong here. I can code these many different ways. A very simple way is a fixed length code, where I take 2 bits for every outcome. Clearly, this is a uniquely decodable code, because if you know the encoding, for example, A becomes 0, 0, given the encoding, you can uniquely reconstruct the outcome. Every encoding maps to just 1 outcome. Here, the length of an outcome is 2 for every outcome. But of course, you could work with many other codes, and we will see examples of that in a moment. So now we come to this relation between code length and probability. So suppose I have an arbitrary probability distribution defined on a countable set. Then the sum of all outcomes and the probability of the outcome is 1, so also small or equal than 1. Now, if I have many different outcomes, then on a very vague, intuitive level, somehow most of these outcomes must have small probability. Otherwise, I can't add to 1. I'll add to something larger. So many different outcomes, most of those must have small probability. On the other hand, suppose there's a code. Suppose it's a code defined on binary sequences of length n. We've already seen that no matter what code you use, only a very small fraction can be compressed by that code. Different codes can compress different fractions of different outcomes, but the number of outcomes that can be substantially compressed is a very small fraction of the total number of outcomes. So for distributions, most outcomes must have small probability. For codes, most outcomes must have large code lengths. This suggests, perhaps, that there's some kind of analogy between codes, or rather their length functions, and probability distributions, and it turns out that there really is. We can make the relationship mathematically precise. So suppose I have some uniquely decodable code of a countable set, and no matter what this code is, there exists a distribution such that for all outcomes, the number of bits needed to encode that outcome minus log probability of the outcome. So small code length becomes large probability, and vice versa. Note that I write P sub C, so different codes write to different distributions, such that this holds for all outcomes. Now, I cheated a little bit because this may be a defective distribution which adds to something smaller than 1 if you add the probabilities of all outcomes. If the code I start with has a particular property which is called completeness, then actually the corresponding distribution will add to 1. And if I don't tell you otherwise, in all these lectures, all the codes I'm going to be talking about will be complete. So then you can assume that the code can be mapped to a probability distribution. Now I just mapped code length to probability. It turns out it can also go the other way around. This has also been proved by Kraft, famous Kraft inequality. So suppose I have some distribution of a countable set, then there always exists some code, different distributions with different codes. Is that for all outcomes, the number of bits needed to encode the outcome is equal to minus log probability of the outcome, rounded up to the nearest integer, because code lengths always have to be integers. Now I will explain this to you in more detail what's going on here in a moment, give you some intuitions about why it's true. First, this. This is the most important thing I'm going to tell you in all 4 lectures. There exists a one-to-one correspondence between probability distributions and code length functions. Small probabilities correspond to large code lengths and vice versa. So that for all sequences, so look, now I'm looking at sequences of length n, in a larger space called sequence of length n. If I have a distribution of those sequences, then there exists a code such that this holds for all the sequences, and vice versa. So, an example is, suppose I have a sequence of zeros and ones. I'm contemplating different distributions as explanations for that sequence. Now, if the distribution, some distribution I contemplate, suppose it's a first order Markov chain, it gives me a certain probability for every different sequence. Now, if I map that distribution to the corresponding code, and then I look at a particular sequence, which I might get in some statistical experiment, then what it says is that if the distribution I'm contemplating is a high fit to the data, the probability of the data under that distribution is large, then the code length under the corresponding code will be small. High probability, small code length. So, in other words, what happens here is that the notion of non-likelihood is transformed into code length, or minus code. So I'm not going to prove formally this correspondence between distributions and codes, but I am going to give you some intuition why this might be the case and what's going on. So let's go back to the previous example. I have 4 outcomes and I have the uniform distribution. If I look at the code I introduced earlier, the 2 bits for every outcome, that clearly I have 4 outcomes minus log probability of the outcome is the number of bits needed to encode the outcome. It's 2, right? Probability is 1/4 under the uniform distribution. And the number of bits needed to encode the outcome is 2. So if I start with this distribution, I can construct this code. Actually, there are many other codes which will satisfy the same thing, because if I swap 2 code words, I will still get it. Reversely, if I start with a code, for example this code, I can get a distribution for which this holds. Now let's look at a slightly different example. Now let me first look at this. It will be convenient to think of codes in terms of binary trees. Now, for the time being, I'm going to restrict myself to prefix codes. These are codes such that every code word, so it's a mapping of some outcome to a binary sequence. If it's a code word, then no other code word can be a prefix of it. If you think about it, those codes clearly are always uniquely decodable, because a decoder can decode all the bits from left to right, and whenever the sequence he gets turns out to be a code word, he knows he's done encoding because he knows that no extension of the sequence can be another code. So then the resulting code is uniquely decodable. Now, prefix codes can be represented by binary tree as follows. Suppose I have a particular code word. If the first bit of the code word is 0, I go to the left. If it's 1, I go to the right. And I look at the second bit. The second bit of the code word is 0, I go to the left again. The second bit is 1, I go to the right. So the code you see earlier, if I encode the letter A in the tree, I go left, left. If I encode letter B, I go left, right, because B is encoded in 0, 1. If I encode C, I go 1, first to the right, then to the left. Same for D. So clearly I can do this with all prefix codes, even if they have longer length, then the tree gets deeper. So here's another example. Suppose I have code just over 3 outcomes, where I encode A as 0, B as 1, 0, and C as 1, 1. Clearly that's uniquely decodable. If I go to code word, look at the first bit, this is a 0, okay, and it was an A. If it's a 1, okay, I have to look 1 further, if it's 1, 0, it was a B. So I decoded C, if it's 1, 1, it was a C. So this is a uniquely decodable code. Once again, I can draw a tree for this code like this. Now, note that for this code, I can associate the distribution of the 3 outcomes as follows. I put probability 1/2 on A, 1/4 on B, and 1/4 on C. So what you see then is that for all outcomes, to just 3, minus log probability of the outcome is code length of the outcome. Minus log probability of A is minus log 1/2 is 2. Minus log probability of B is minus log 1/4 is 2. And the number of bits needed to encode B is 2 in this code. So here I have this equivalence between code length function and distribution, again with equality. I start with this code, I can construct a distribution which has this property. Now, in these pictures, you might have spotted some general idea. So suppose for the moment here that we're working with a prefix code. Now we're going to map that code to a distribution such that this minus mod probability is code length code. How does it work? Well, if I have an arbitrary binary tree, I denote by for every leaf by the depth of the leaf, the length of the path between that leaf and the root node, then I always have this sum of the 2 to the minus the depth, the length of the root to that node, to that leaf, is more equal than 1. So note that we have this here. 2 to the minus 1 is 1 half, plus 1 fourth, plus 1 fourth is 1. And we also had it here. Here we have 1 fourth, 1 fourth, 1 fourth. It's always 1. And it's actually very easy to see that this was always 1 because you can extend any tree to the full binary tree as we get to that. And then clearly the number of leaf nodes is equal to 2 to the minus depth of the tree. So it must sum to 1. So with this insight, with the fact that each prefix code can be mapped to binary trees such as the leaf nodes represent all the important symbols, I now know that for my prefix code I must have that sum 2 to the minus L of x, where x is something to be approached, must be smaller or equal than 1. Now, if I now make a distribution, Lx is minus log px, then I simply get sum of px over all x is smaller or equal than 1. So here I constructed a distribution starting with a code length function as a prefix code. Now it turns out that every uniquely decodable code can be viewed as a prefix code. If you have a uniquely decodable code, there's always some code which gives the same code length to every possible outcome, which is a prefix code. So together, this is MLSS theorem, this is Ruff's theorem. You have that every uniquely decodable code can be turned to a distribution. I can also go the other way around, as I said. This is a bit more complicated. I will not show it to you in detail. I'll just give you some idea what's going on there. So suppose we get once again 3 outcomes and I have a distribution over them which is uniform, probability 1/3. So now I want to construct a code such that the number of bits for any outcome is equal to minus log probability. Because minus log probability of an outcome is minus log 1 over 3, which is log 3. Which is not an integer. Clearly, I can't make a code which satisfies the number of bits in its important outcomes log 3 for all outcomes. However, I can use the same code I used before, where I code A is 0, B is 1, 0, C is 1, 1. And then you can easily check that this will still hold. Minus log probability of an outcome. This is 2 or 1, depending on the outcome. This is 2 or 1, depending on the outcome. So it's 2 for B and C and 1 for A. This is minus log 1 over 3 is log 3. The difference is always smaller than 1. So the theorem does still hold. Start with a distribution, I make a code, which is this holds. Now, if I just have 3 outcomes, then this is not very meaningful because the code length compared to the difference between minus log probability and code length is not small. They're about the same size. And now if I have even for reasonably small n, say n is 10, suppose I have 10 outcomes, and I look at a distribution over 10 outcomes. So for example, it could be the uniform distribution, so then I have 3 to the power 10 different outcomes, and the probability of each of them is the same. It's 1 over 3 to the power n. The minus log probability of all outcomes is n log 3. Now naively it might seem that if you use the code which you just used and you extend it to n outcomes, that for some outcomes, like for example the sequence of all C's, you need 2n bits, which is a lot more than n log 3. Right? It's on the order of n more. But this is not so, because you shouldn't construct the code corresponding to this distribution based on concatenating the simple code. Rather, you should directly look at the large space of 3 to the power n outcomes. Within that space, you can map the distribution of all sequences of that length to a code such that you have code length is minus log probability plus maximally 1 bit. And then since the code length is on the order of n, the difference between minus log probability and the actual code length you need if you use the code corresponding to the probability is completely negligible compared to the total code length. What you're going to do then is you're simply going to neglect the integer requirement for code length. And this is another very important thing. Many papers in information theory, people work with idealized codes, and this is always the case with MDL. So we never work with real codes which must have integer code lengths. You always forget about the integer requirement. In fact, in many papers in IEEE information theory, the words code and distribution are even used interchangeably. People might refer to a code and call it a distribution, and what they mean is this method, or vice versa. It took me a very long time to figure out what is meant. This is what they do. Now, note that I haven't said anything about anything generating data. This is a purely formal correspondence. I treat distributions simply as functions in a countable set which have to add to 1 and which are non-negative. Those functions can be mapped to code-length functions and vice versa. Right? So there no interpretation whatsoever should be given to those probabilities. Another important thing is that you can do the same thing if you have continuous outcomes by discretizing them, and then you get an analog of this correspondence which I've just seen. So what I'll do in the remainder of this lecture, sometimes I will use the symbol P for distribution of continuous outcomes, and then I will use the same symbol P with a bad overload notation for the density. And implicitly, what will happen then is that you discretize outcomes, and you look at the code corresponding to discretized outcomes, it won't be important for the things I'm going to do. So this is about the correspondence between probability distributions and code lengths. Now I'm going to apply this for universal models. And what are universal models? To explain that, I first have to explain universal codes. Now, universal code works like this. Suppose I have a set of codes. Think for the moment I'm financing the codes. And I get some sequence of data. And before seeing the sequence, I think that one of my codes probably will compress the data a lot. So it might be a good code to use if my goal is compression. Now, what I want to do is that now I get real data, particular data, and what I want to achieve is that no matter what data I get, I encode the data using a lot more bits than the particular candidate code I have, curly L, which is best for that particular sequence. So for some sequence, this code might be better. For other sequences, that code might be better. In the sense of giving a shorter code length. I want to use the best code no matter what sequence I get. Now, if I'm only interested in code lengths, I should talk about the set curly L should be thought of as a set of length functions corresponding to the code. So I'm not interested in the details of the code, just in the lengths for different sequences I get using a particular code. It's like what L rather than C. So suppose I have some finite set of codes. I want to compress data as much as possible using any of these codes, so I want to use the code which is best for the particular data. How am I going to do this? Well, it's so trivial. You simply pick the code which is best for the data and code your data with that code. Unfortunately, this does not work. Why doesn't it work? Well, to see that you should realize that you can always think of encoding and decoding as a game between the sender and the receiver. Sender and receiver means when they agree on a particular encoding description method. And that's before seeing any data. Then they go to their respective homes again. The sender sees some actual data, X. He encodes that using the codes. He sends the encoded version to B, and B has to decode it using the code to which they agreed before. Now, if the sender gets the data and simply uses the code, which gives the shortest code to the data to encode the sequence, the decoder cannot decode it because the decoder only knows the set curly L, which they could have agreed on that beforehand. But he doesn't know which element of the set curly L the sender has used because the sender used the one which was best for the data at hand. So the decoder doesn't know what code is being used, so he can't decode the message. So there's a problem here. You can't just pick the code which is best for the sequence at hand. But now it turns out, it's kind of magic of information theory, that there exist codes which, no matter what sequence you get, are almost as good as the code that's optimal for that particular sequence. So it's almost like like using the code which is best for the sequence. You have the code which is best with hindsight, after seeing the data. Now such codes are called universal codes relative to the set candidate codes for the L. And of course, this is not a formal definition, just to give you an intuitive idea of what a universal code is. Here's an example. Suppose curly L is finite. Let's say I have it has m elements, so I have m possible different ways to encode data. then one thing you could do to encode and send data in a way such that the decoder can decode it is to first send an index saying what code in the set PL you're going to use to encode the data. Then if you first send the index, the decoder can first decode the index, and the decoder knows what code you have used to encode the data. And then it can decode the actual data. So if this, let's say you have m elements here, you could encode an element in here by giving its index some enumeration. And that will take log m bits, right? You take the uniform code we talked about before. To encode 1 out of n possibilities, you need log m bits. So if you think of k is equal to log m, the code you get, the sender does is simply look at what code is the best for the sequence I have. I first encode the sequence with that code, then I encode the sequence itself. Then you first do log of m bits, and then number of bits for that sequence for the best code for that sequence. So then you get a real code which can be coded. The sequence can be decoded no matter what sequence you get. And the number of bits needed to encode the sequence is always more equal to the best for that sequence plus log of the number of lines. The crucial thing is that this log m does not depend on the length of the sequence, whereas typically for codes we encounter in practice, the number of bits needed to encode the sequence of length n grows linearly in n. So for small sequences, this is not very useful. But as your number of sequences grows, this becomes extremely useful. Because, for example, if you have 100 different codes, then this will always be 100, and as large as will be something times n. In particular, on average, per symbol that you have to encode, the difference between you and someone who knows what is the best code with hindsight, after having seen the sequence, the number of extra bits you need goes to 0 at order 1 over n, which is very fast. So now we're going to move from universal codes to universal models. Yeah, sure.
So if k does not depend on n, but now for longer sequences, to be able to compress many different longer sequences efficiently, you're going to need a larger set L, turns out.
Sure.
And then you need a larger description and hopefully L anyway.
Of course. But I'm going to get to that later. For now, I'm just saying, suppose I have a finite set fixed once and for all, and I'm going to see what happens. But you're right, because if you want to have a rich language in which you can compress many sequences, you will have to have that grow and as well.
So my question is, does that also then scale with n linearly or not?
We'll see that. We'll see all of that in the next lecture. Typically, it's logarithmic. So now instead of a set of codes, I have a set of distributions. Think, for example, of Bernoulli distributions, biased points. So borrowing some basic notation, I can note these distributions like this. So for example, I have, this is the hypothesis that the probability of a 1, a binary sequence, hypothesis probability for 1 is 0.2. Probability of 1 is 0.4, 0.6, and 0.8. I have 4 different probability distributions. They all assume data are independently distributed with different probabilities of 1. That would be one possible example. There are 4 distributions. Now, if I start with those 4 distributions, then clearly I can map all of these to codes such that for every single distribution, the number of bits I need to encode a particular sequence is equal to minus log the probability for that sequence. So if I get a sequence with frequency of 1, so about 0.2, then the distribution, which has probability of 1 about 0.2, will give a very large probability to the sequence. And I'll have minus log the probability of the sequence according to that distribution as my code there. If the frequency is closer to 0.4, then the distribution which has probability from 0.4 will be the largest probability and therefore the smallest probability to the sequence. Now, mapping all these distributions to code in this way, I know that I can also make a universal code where I first index what theta I'm going to use for encoding, then I map that theta to a code, and then I know that no matter what sequence I get, the number of bits I need to encode the sequence is minus log probability of the sequence plus k. If I have 4 distributions here, then k will be 2. So that in particular, I need less bits than the theta, which gives the largest probability, therefore the smallest code length, the smallest code length of the sequence plus 2. So starting from distributions, I construct the universal code can map back if I want. Here I map from distributions to codes. Here I can map from codes to distributions. I know that if I have this code, there must be some distribution, such that minus log probability that that distribution assigns to sequence output is more equal to minus log probability to sequence plus a constant. Now, by exponentiating on both sides, I see that it simply says that there exists some distribution of a sequence of n that dominates all elements in curly f. So this distribution gives more than some constant times the probability of the sequence according to this distribution, where it's constant, does not depend on n, whereas typically these probabilities are exponentially smaller than n, right? And increases, data are independently distributed, is exponentially smaller. It's a product and probability. Now, intuitively, such a dominating distribution corresponding to universal code will be called a universal model. Now there's some terminological problem. Because in statistics, a model typically denotes a family of distributions, like the model of all Bernoulli distributions, or the model of all first order market chains. In information theory, a model stands for a single distribution, like the Bernoulli distribution is probabilistic 1 and 0.6. And a model class is used to denote a set, family of distributions. Now, I want to stick to statistical terminology because that fits more with this summer school, but terminology universal model, which refers to a single distribution, is so ingrained that I can't back away from that. So in my terminology, a universal model is a single distribution, like in information theory, that represents a set of distributions, which is itself a model, but in a statistical sense. It's a family of distributions. So universal model is a single distribution representing, dominating a whole set of distributions. Now we've seen already an example of the universal model, which was the so-called two-part code, where you encode data by first encoding an index and then encoding the data using the code corresponding to the distribution index by your index. But it's by no means the only universal code or model. So another example are Bayes mixtures. So suppose once again I have a finite set curly n here. They have prior of the set, so that's the distribution of the distributions in here. Now, Bayesian marginal likelihood is defined as probability of the data relative to this model is the weighted probability of the data according to the elements in this model times the prior of a particular element of the model. So it's easy to check that this forms the distribution of all sequences. It's the weighted average of all the distributions. This is, of course, basic notion of Bayesian statistics, and it's easy to show that it's a universal model. Because for all data of any length, I have the minus log probability of data according to the Bayesian model, Bayesian universal model, is by definition minus log of this weighted average, sum of all outcomes. And that is, because the sum is larger or equal in each of these terms, minus log of the sum smaller or equal than minus log of each of these terms. This means that minus log of this probability, according to Bayes, is smaller or equal than minus log of probability according to any theta in this curly n. So any of the distributions I'm looking at, plus something which does not depend on your data. For example, if this is finite, you have 4 elements, for example, you take a uniform prior, probability of each element is 1/4. The minus log 1/4 is 2 again. So the probability is minus log probability is smaller than the minus log probability according to the thing that fits the data best, plus 2, which again does not depend on the size of your data. So this is another universal model which we've already seen, two-part code, which you can also think of in this way. You first use a prior distribution, which you can, where here you can map the prior distribution to a code, such as code lengths are minus log prior probability. So then, if you encode the index of the theta that best fits the data, which is just the maximum likelihood estimator, maximize the probability of the data, and then you encode the data using the theta, then what you do is minus log probability, prior probability of the theta you use for encoding, minus log probability of the data according to theta. So here again, this is a constant for this increased linearly. Now there's a big difference between this two-part model and the Bayesian universal model, because here we have equality. Code length is exactly equal to this. In the Bayesian model, you have an inequality which will typically be strict, because here we have minus log of the sum of all these probabilities, and if none of these probabilities is 0, that typically happens, then minus log of the sums actually really not just smaller equal, really smaller than minus log probability of data minus log of the prior. So this gives, for every sequence, this gives code lengths which are at least as small as those given by the two-part code. For most sequences, it will actually give smaller code lengths. So in this sense, the base universal model is better, right? Better than the two-part model. It gives smaller code lengths to about every sequence, and longer code lengths to no sequence. This raises a number of questions. First of all, what prior would be the right prior to use here? Because there are many different Bayesian marginalized groups. Depending on the prior use, you get something different. Another question is, okay, there's the base universal model, two-part universal model. Maybe there is more universal models. If we have two other candidates, how do we know what is a good universal model and what is a bad universal model? So this now comes to the key of model version of MDL. We're going to define the optimal universal model. We define optimal in the minimax sense, and that means the following. We were always looking at a distribution that gives essentially as much probability for every sequence as a particular distribution in your model. It gives the highest probability to the sequence. So our goal was to find a distribution, or including the appropriate length, so this difference is small, no matter what sequence you get. Right? Clearly there is no distribution which makes this difference zero for all sequences, because if theta hat maximum likelihood is different for different sequences, which it will be if there are more than one distribution in your set of distributions, then this doesn't form a distribution. If you sum this over all sequences, relative to data according to the thing that's best for that particular data, you will get something larger than one. So there's no distribution, so this is zero for every sequence. So alternatively, you might look for the distribution or equivalent code, which minimizes the difference in the worst case of all possible sequences. So you look at all possible sequences, you look at what's the worst that can happen here. You know that that must always be larger than zero, and then you pick the P star to minimize the difference. Now it turns out that you can actually solve for this P star, which is pretty easy to solve for. And you get something which is called the normalized maximum likelihood distribution, or the Starkov distribution, because Starkov is the first who came up with it in a different context. And that's again a distribution relative to a given set of distributions, which will make it the representative of this whole set of distributions. Defines this. For every sequence, the probability assigned to the sequence is simply the probability of the best fitting thing for that sequence. But as we've seen, if you sum that over all sequences, it doesn't sum to one, it's something larger than one. So it's not a distribution. So what you can do is you normalize. You simply divide by the sum of all possible sequences relative to sequence according to the maximum likelihood distribution for that particular sequence. Now you have a distribution. If you plug this distribution in here, then it's easy to show that the supremum over all data becomes a constant because you get a minus log this thing term here and minus over this thing, so it cancels. So what you end up with is log of this thing. It doesn't depend on x, so it's constant. And that actually means, because it's constant, no matter what data you get, it must achieve the minimum in the worst case. So this is the optimal universal model. And now I'm nearly done. I'm just going to say that this is the basis of modern versions of MDL. And in a very simple case, where you have, let's say, two models you want to select between. For example, the set of all Bailey distributions with different parameters for your data, or the set of all first-order Markov chains, where the probability for one depends on whether the previous bit was a 1 or 0. What you would do is the following. You have two different models, one of them intuitively more complex than the other. Now, MDL tells you to pick the model such that the associated optimal universal model relative to the model gives the largest probability to the data you actually have. So you pick the model such that the maximum of all models of the probability of the data according to that model, well, that's the one you pick. So relatively you pick the model which minimizes minus log according to the data according to that model. Now, if you write this in its minus log form, because its distribution is a fraction, minus log probability data according to maximum likelihood plus log normalizing term. So taking the fraction and log into a sum, it tells you to pick the model which minimizes minus log probability data according to the maximum likelihood distribution for the data, plus log of an enormous sum over all possible sequences of data of the probability of that sequence, given the maximum likelihood distribution for that sequence. Now, Intuitively, the first thing can be thought of as an error term because the best fitting distribution within your model fits your data. The higher this probability, so the smaller this might probability to solve the error. The second thing can be thought of as a complexity term. I'll say a lot about that next lecture, but for now let me just say that if there are many distributions in your model which give a very high fit to your data, so your model can explain many patterns well, there's a large list of problems get in, and the sum will be very large because there will be many sequences with a probability almost 1 in the sum of all sequences. So in the extreme, for every sequence there's a distribution which gives a probability 1. This will be log n, log 2 to the power n, and the complexity term will be n. In the other extreme, if there is one distribution, the sum will be 1, and the complexity term will be 0. So the second thing acts like something like a complexity term, and the whole procedure of fitting this distribution can be thought of as minimizing a trade-off between some way of measuring the goodness of fit of your model, according to the best fitting distribution in the model, plus something like that measures complexity in some way. So this is actually what I have to say for today, and the next lecture we're going to spend the whole lecture analyzing what's going on.